Complex analysis and topology are two subjects that have grown up together and are very intimately connected. And so what I want to do now is give you some looks at the high points of that connection, no pun intended, as you'll see, and show how having a uniform, no pun intended, language for talking about certain concepts can be very useful. So when we start talking about arcs and conformal mappings and the like, we'll be using this topological language to help us say things more compactly, no pun intended. So the basic idea of topology is open set, and that's a direct generalization of what we talk about in the complex plane. In the complex plane, what we get is, and the same thing in the reals, everything is based on open balls. And so a set is open if every point has an open ball around it. And so the open balls, they're sets that look like this, where the absolute value of x minus a is less than some radius r. Very important that it's less than. And so that's an open ball. In the complex plane, that's the complex absolute value. In the real line, that's the real absolute value. And that's called a metric. And you can go way off into lots of rabbit holes. I guess rabbit holes go this way, worrying about what metrics are. But we've got one, so we don't have to worry about finding one. We've got one. And so the thing with open sets is that an infinite union of open sets is open. An infinite union, any union that you like, an arbitrary union. But if you start taking intersections, if you do too many, you can get a non-open set. So we can only do finite intersections. And there's a real simple example in either in the real numbers or in the complex numbers. Like if you take your open set u sub n to be the ball about 0 of radius 1 over n. So that's by definition an open set. This is pretty common notation for ball. So this is, the radius is 1 over n, the center is at 0. And if you intersect all those, the intersection is just the point 0. That's not open. There's no ball inside the origin. And so there's the failure. So you can only do finite intersections. This comes up every now and then. Okay. The big advantage we get from talking about things this way is a widespread abstract definition of a continuous function that simplifies so many things in everything in mathematics. So f is continuous, drum roll please, because this is one of the most important definitions that we've got. If the inverse image of an open set is open, the inverse image of every open set is open. This covers a lot of domains, a lot of ranges, a lot of different ways of having the topology, but this is the uniform, no pun intended, definition of open set, is that it takes open sets in the range, and when you pull them back, they're open too. Now, in the complex or real numbers, an open set in the range means that you've got a ball. That ball has radius epsilon, and when you pull it back, you should be able to get a ball around the point. That ball has radius delta. So this is a direct generalization of the epsilon delta idea for continuity without having any need for measuring. I warn you, there are some places where the idea of open set gets to be quite woo-hoo, but we're not going to bump into them in this course. Okay. So the two big definitions that happen that are useful to us are connectedness and compactness. And I've already talked some about compactness because the idea with compactness is that every open cover, boom, 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 has a finite subcover, boop, 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 boop. That's what makes a set compact. And so in particular, if you've got a lot of balls of convergence of power series, oh no, you only need a couple. Well, you might need a couple of million, but you only need a finite number. And that replaces this expansion of a function using power series by a finite number of expansions, which is going to tie up with uniform continuity. Okay, well, everyone tries to define connected. A set, a region, something, a space, X, is not connected. It's so much easier to define the negation of this if I'm going to write this. I'm going to use some pretty standard notation. And that is this. And this is, of course, this means disconnected. So what we have is X is disconnected if we can write it as a disjoint union. This funny little union sign means disjoint. So A intersect B is empty. Neither A nor B is empty, and they both have to be open. So the picture that goes with this is a not connected set. It's got two components, that's the word. And so I should label these things. You've got an A and a B, and they're each open, and they don't meet. And that's obviously not connected. Now, you can get into some bizarre stuff with limit points and the like, but we'll worry about that when we get to it. So connected means that you can't partition X this way. Pretty clear. There's a theorem in alphors that says a set in the complex plane is connected if you can draw a polygonal segment between any 2 points. That's a nice practical way of expressing it, but that's still working on this, and he goes through some detail onto why that's true. Okay, X is compact if every open cover has a finite subcover. That means every wickety-whack, crazy, man, you've got to be kidding, there couldn't possibly that many be open sets in the whole universe. Just need a few. And we have talked about that. So you just need a finite number of open sets to cover X. Even though you're given an infinite number, you can throw away almost all of them. So that's called a finite subcover. Okay. So that's the definition of compact. The big thing that we get out of the topological definition of continuity, inverse image of an open set is open, is this. If X is compact and F is continuous, then F of X is compact. That's a pretty easy kind of diagram chase kind of proof. So you cover the domain, pull it back, you only need a finite number, boom. Cover the range. And so a continuous image of a compact set is compact. And in line with that, if X is connected, then, and it's almost the same proof, and F is continuous, then F of X is connected. And it takes a lot longer to write this than to say it, sorry. Should have told you to go out and get a snack. So these are two big ideas. That's what we get out of this uniform topological definition of continuity. That means when you're like mixing domains, when you're talking about an arc in the plane, the domain is an interval in the real line, but the codomain where the arc is the plane, and you still have this same topological language, and so things work out quite nicely. Okay. So what about uniformity? Uniformity requires a metric. You need to have something that's do that. So first of all, there are two things. F is uniformly continuous. Now you just can't define this anywhere. You have to have this distance function, which we have. So F is uniformly continuous in some region if for every epsilon, I'm skipping some of the subtext, there exists a delta such that for every A in the region that we're talking about. If x is within delta of a, then f of x is within delta of f of a. I'm sorry, within epsilon. So the thing is, where you're using the metric is you're going to use the same delta for every point. In ordinary continuity, you could use a different delta at every point, but here we have to keep using the same one over and over and over again. It gets tired, I know, but that's okay. The other thing that we have is uniform convergence, which is why is uniform convergence important? Uniform convergence is important because the uniform limit of continuous functions is continuous. That's one of the big deals in real analysis, and we're going to use that here because the uniform limit of continuous functions, well, now that preserves compactness and connectedness. Those are important things to preserve. So I'm just going to write that down. Fn converges uniformly to F if, and again, we need to use the metric here. For every epsilon there exists, now there's going to be a capital N, such that for every A in the domain, pick an N, and then every A works. That's the same N works everywhere. If the absolute value of F sub n of x minus F sub n of A, the distance between F sub n of x and F sub n of A, excuse me, I'm saying this backwards. Screaming sacks used macaroni, forgive me. If little n is bigger than big N, then the distance between F sub little n of x and F sub little n of A has to be less than epsilon. Same N everywhere. So you go that far out in the sequence and boom, you've got this continuity is guaranteed, which means connectedness is preserved. That means compactness is preserved. That means that we're going to have nice things to be able to say about the functions that we use in this context.